Hello everyone, so I'm going to be doing another video still on the energy topic, and today I'm going to focus on work and energy. So we know the types of energies. We know that energy is never created or destroyed, it's only converted or transferred. So now we are going to look at the more mathematical part of this energy and work, okay? First of all, work is energy transferred. You need to know this by heart, because what is going to happen is many times you're going to find exercises where they give you the data for you to calculate work and they ask you for a type of energy that was transferred, or the other way around. They give you, for example, mass and velocity, which gives you to calculate kinetic energy, and they ask what was the work done, okay? So work is energy transferred. If you think about it, in lessons, when I give you like lots of homework and stuff like that, you guys are like, oh, this is so much work, right? Now, what you're trying to say really is that you need to convert a lot of your chemical energy into the kinetic energy for you to be moving your pen and writing the things on the paper. So there you go. You know that work is energy transferred, okay? So work in joules is the energy transferred in joules as well. Work done by a force can also come with a formula. So the work in joules equals the force in newtons times the distance moved in the direction of that force, and that distance is in meters. So if you have a situation where the force is perpendicular to the distance that an object moves, for example in circular motion, no work is done on that object, okay? But any other stuff, like pushing a car, for example, then the work that you do, the energy that you transfer as you get that car to move, is the force that you apply times the distance that the car moves in the direction of that force. You also need to know the formulas for gravitational potential energy. Now, this energy is an energy that is because an object has the potential to fall due to its position, and it has the potential to fall because the Earth's gravitational field is pulling it, okay? So if an object is moving up, then the gravitational potential energy increases, and the increase in GPE, gravitational potential energy, is equal to the work done by lifting the force. This assuming that the system is 100% efficient. There is always some energy that is going to be transferred towards heat or sound, so there's always some waste energy. When an object is moved down, the gravitational potential energy decreases, and the decrease in gravitational potential energy equals to the work done by the force of gravity acting on the object as it moves down, okay? So there are two ways that you can calculate gravitational potential energy, okay? Or to calculate the work done by moving an object up or down. So it depends on how much you move vertically times the weight. So it's the force that you move times the height, the distance that you moved in the direction of that force. It's just like the formula for work. So change in GP in joules equals the force that you have, the weight of that object, in newtons, times the height, the distance that you moved up or down, okay, in meters. However, sometimes they give you exercises without telling you the force, but telling you the mass of the object. Now, if you need to calculate GPE in that case, what you do is remember that the GPE is going to be the mass in kilograms times G, the gravitational field strength of the Earth, 9.81, which comes in newtons per kilogram, divided by, times the height that you moved in the direction of the force in meters. So basically what I'm saying is that the force in newtons equals the mass in kilograms times the G, the gravitational field strength. Okay, so we know the formulas to calculate work, we know the formulas to calculate gravitational potential energy, and we know that work is always energy transferred. I can also have kinetic energy. I need to know that formula as well. And the kinetic energy comes in joules because it's an energy and is equal to 1/2 of the mass of the object times the velocity that the object is moving squared, and the velocity is in meters per second, and the square should be out of the brackets. The whole thing goes squared, okay? So And one common mistake of people is writing the formula and forgetting the square, okay? And doing 1/2 of mass times velocity. Do not do that, because otherwise you get the whole exercise wrong, and we cannot even give you marks for the working out because you don't have velocity squared. So the kinetic energy is also equal to the work done, okay? So the work in this case of the making a trolley to move, is the change of the trolley's kinetic energy is equal to the work that the guy does on the trolley. In reality, as I told you, trolleys, cars, all of these things will always have some friction. So there is always a smaller change, okay? Not all the work that you're doing is going into the form that you want. So not all the work is going to be into gravitational potential or into kinetic energy, because some work is done to overcome friction, okay? So you always have some work, some energy wasted as heating and sound, okay? Finally, elastic potential energy is the last formula you need to know. Oh, actually, I have another one, sorry. So the elastic potential energy is an energy that is stored whenever you stretch something that has an elastic property, like a rubber band, or here with, I forgot the bow and the arrow. So the elastic energy is usually transferred into kinetic energy, also to gravitational potential. And it has the following formula: elastic energy equals 1/2, just like kinetic energy, times K, which is the constant of whatever you're extending, spring or rubber band or elastic constant, times the extension squared, okay? The extension that you had. Basically, is the same formula as kinetic energy, but instead of the mass, which is a constant of the object, is the constant of extending the object, the elastic constant per se, spring, elastic, as I told you, any constant, times, and then instead of being velocity squared, how much you extend squared. So the extension is in meters, the energy comes in joules because it's joules. The spring constant or the elastic constant is Newton per meter. So how much force you need to do to get 1 meter of it to move, okay? So if an object is elastic, if is going to regain the shape after being stretched or squashed, and more on that on Hooke's law, okay? And the elastic potential energy is the energy that is stored in an elastic object when work is done on it to change its shape. Again, the difference or the change of my elastic potential energy is the work that I did on the object. Work is energy transferred, okay? Finally, I can say or I can give characteristics of the power of something, because power is the rate, so how fast energy is being transferred, so how fast I'm applying this work, okay? So power that comes in watts, W, equals the energy that I'm transferring in joules, J, divided by the time taken, and it needs to be in seconds. Many questions give you the time in hours or minutes. You need to convert it into seconds. I can also say that power equals the work done over the time taken to do that work, okay? Because energy transferred and work done are the same. I don't know how many times I said that, but I must have said it about 5-6 times already, okay? So that is it for today. I have just a quick exercise for you if the sentences are true or false, okay? So let's look at them. Gravitational potential energy of an object depends on the weight only. No, it depends also on the height, okay? For the same height, the object with a larger mass will have a greater gravitational potential energy. Yes, because GPE equals the mass times the gravity times the difference in height. GPE increases when an object goes down and decreases when an object moves up. Is the other way around. I increase GPE if my height increases. I decrease GPE if my height decreases. Work is the same as energy transferred. Yes, I said that several times. Energy equals power divided by time. No, power equals the energy divided by time in seconds, okay? So that is it for today. I hope it made sense, and more revision videos will be coming soon on the energy topic. Up to then, keep happy and healthy. Bye!